Welcome to the online tutorial series of distributed DBMS. In this video, I will explain concurrency control and scheduling with context of transaction management. I am Jishan Sheikh, Assistant Professor in IT/ICT Department of LJ Institute of Engineering and Technology. So let's see today's topic, what I am discussing: concurrency control, scheduling and distributed serializability. So when we are talking about concurrency is a basic part of our asset property. In asset property, I already discussed in brief what is exactly concurrency is and what are the degrees are achieved by any database if I want to consider that is a good DBMS. So if our particular transaction is utilized more than one shared resources, at that time we have to achieve concurrency. So let's discuss what is the exactly concurrency control and what are the anomalies for that. So when the problem of synchronizing concurrent transaction such that the consistency of database is maintained while at the same time maximum degree of concurrency is achieved here. So here degree 0, 1, 2, 3 is considered here. So when we are achieving maximum type of degrees here, then we can say that we can achieve the concurrency control. But if we are not maintaining that type of degrees of concurrency, then we are facing the anomalies problem. So anomalies may be lost update anomalies and it might be a inconsistent retrieval anomaly. If we are talking about lost update anomaly, the effect of this anomaly on some transaction which are not reflected on the database. For example, if any transaction is updating the data and that updated data is not read by another transaction, that is the case of our lost update anomalies. Second one is inconsistent retrieval. If any transaction is reading the data and after some time the same transaction is trying to read that data, but both the time that transaction is getting the different answer, that can be considered as an inconsistent retrieval. So if we are talking about the controlling of the concurrency, then we have to maintain both these things. Now we are talking about in brief how the scheduling is achieved here. Because if we are trying to achieve the concurrency, multiple transactions are properly use that particular shared resources. So how can we get those data properly? That is the part of our scheduling. Scheduling is also considered as an execution history. So if we track any log of any transaction, if we are checking that which transaction is used, which shared resources for which purpose, if we are tracking that, that will be considered one execution history or one schedule. So in order in which operation of set of transactions are executed, that is known as our schedules. If history or schedule can be defined as a partial order over operation of set of transactions. If we have multiple transactions at the same time and that transaction is performing number of operations at that different time, that set will be decided what are the schedules are generated for this. Consider this example. Here we have T1, T2 and T3, three transactions are available. T1 is performing read X, write X and commit operation. The same way T2 is performing write X, write Y, read Z and commit operation. And our third transaction T3 is performing read X, read Y, read Z and commit operation. So ultimately we are saying that three different transactions are performing some operations. That operations use the some variables that are shared here. We can see here X variable is used by T1 as well as T2 and also by T3, while Y is used by T2 and T3 and Z is used by T2 and T3. Z is not used by T1 and also Y is not used by T1. So how can we exactly schedule this algorithm? That is our main aim to find the concurrency. So here number of transactions are performing the operation of reading and writing. We can write that in the term of history. So here H1 is a set of operations that are performed by our transaction. So here we can write that write Z of X. We can say that particular second transaction is performing write operation in variable X, WZX, meaning that Z operation is performed by this particular operation. The same way I can write that R1X. R1X is understanding by transaction 1 is performing read operation on my X variable. So the same way the number of operations are performed by the transaction are put in one set. That set's schedule is known as a execution history. So how can we properly manage this history? So for that, DBMS is providing DAG, direct access graph. So what the particular transaction is performing the operation, that is translated into the graph form. So we can say that here my write to X, W2 of X operation, after that my read operation R1 is performed, and on the basis of that my R2, R3, X operation is performed. The same way we can say that after reading of X operation, my T1 transaction is performing W1X operation, and after that it is committed. The same way for my T2 operation, we can say that W2X is writing the operation, then again it write the Y operation, then it read the Z, and then it commit that operation. The same way T3 is performing the operation of reading of X, Y and Z, and finally commit the operation. Now, what is the exactly scheduling is performing here? Till now, what we are seeing, it is all about how the exactly transaction is performed for that operations. But if we are trying to convert this particular DAG graph into the schedule, then we have to use the prefix here. So a schedule is a prefix of complete schedule, such that only some of the operation and only some of the ordering relationships are included here. So unnecessary, we are reducing some relations that are generating one cycle here. So from this our DAG graph, I am creating this particular graph that is known as a one schedule that is maintained by our transaction manager here. Okay, so for this DAG graph, we can create this type of scheduling algorithm. So here W2X is performing yes write operation. But once write operation of X is completed, after that the read operation can perform, because we have to maintain the concurrency here. Because already if any operation is writing something and if we are reading that, then our database may be conflict here. That's why after the completion of write operation, we have to read the data. That's why our first step is here that after the performing of W2 of X, our read operation of X and read operation of R2X can be performed simultaneously. The same way after performing the writing of X operation, our writing of Y operation can be performed by our transaction 2. And the parallelly, if our write operation is performed by the T2, T3 can read this data from our shared data. The same way after performing the write operation of Y, our T2 and T3 transaction can read the Z data simultaneously. If our shared data is read here, then we can easily read, there is no confliction here. So this is the basic idea how serial example will be working. Now we are talking about serial history. So here all the actions of transaction occur consecutively here. So no interleaving of transactions or operations are performed here. If each transaction is consistent here, then the database is guaranteed to be consistent here. So here each and every transaction, what the operations are performed here, they must be in the consistent state. If consistency is not maintained by our particular transaction, then database integrity cannot be guaranteed. So for our above example, we can create one transaction set here. So this transaction set is performed for different T1, T2 and T3. Now we are moving to the next, that is all about serializability history types. So here we can say that it is all about equivalency operations. So here conflict equivalence and here conflict operations are maintained there. So if here conflict equivalence is there, then the relative order of execution of the conflict operation is belonging to unaborted transaction only. If two transactions are there and then transactions are aborted in the particular consequences, then we cannot guarantee that it is successfully committed or not. So that's why we cannot consider here aborted operation. So if two transactions are there in our history, we should take care about that transaction must be unaborted. Now we are talking about the conflict operations. So here two complete operations are that read and write is available here. If both the X is the same data item here, then conflict are there. That's why we have to take care that if we have X and Y value that is shared value might be read or write. If we are performing the read operation of X and that is shared, then it is okay. But if we are performing the write operation on shared data item, then we cannot simultaneously access. So we have to take care about that which operation is performed on our shared operation. That's why we are considering here conflict operation. So finally, if we are concluding conflict operation, then we have to take care about that shared data item is read here. Shared data item is performed by read operation, then it is okay. But shared data item is used for write operation. At a time only one transaction can access those data. From that we can find our conflict and non-conflict schedule here. So for given example, we have two histories here, history of S and history of H1. So this operation cannot be considered as a conflict equivalence because here T2 is performing write operation of X. The same X operation is X data item is read by our T1 and X data item is read by T3 here. So we can see that here in our H1 here. W2 is X here, that is the read by our second operation. Then after our transaction 1 is reading those data, and after that is the read by our X data item. But we already know that the same data item X is read by T1 and T3. So both T1 and T3 can read simultaneously. So there is no conflict occur here. But in our history one we can see that both are not reading those data simultaneously. In the second operation, that is a conflict equivalent here. We can read here W2X, after that R2 of X, then after W1 of X, then R1 of X. So here our conflict equivalence schedule will be maintained here. So according to our theory, if our data item is shared here, then we have to perform read operation, then there are no problem of confliction. If write operation is there, then we cannot perform simultaneously work. So this is the basic idea how serial schedule will be occur. Now last topic of particular schedule is all about distributed serializability. So if we are talking about distributed serializability, then we have to take care about two keywords here, local and global. Because when we are talking about distributed keyword, our data can be occur at one site or multiple site. So if data item is executing at the particular site, then it can be considered as a local operation. But if data access at the remote site, that can be our remote place, then it will be our global. That means we have to consider two type of schedule, or we have to maintain two type of history, local and global here. So for our particular transaction management and distributed side, we have to consider global transaction also here. So for global transaction or global history to be serialized, if two conditions are necessary. First, each local history should be serializable. So when the transaction request is coming for particular site, that site is known as a local site. So local site, each and every transaction must be serializable. Second option, two conflicting operations should be in the same relative order. The order of the operations are here. That operations are already discussed. That might be read or write. In all of the local histories, that Y appear together. So in our local site, that operation must be in serializable order. That tells about the serializability of that particular operations. And if we are considering this type of example here, that is available at the different site T1 and T2. T1 it might be available at X site, T2 is available at the Y site. So here X site is available, X is available at site 1 and Y is stored at the site 2. So here we have to take care about that individually at site 1 and 2. Both the site must be serializable, and when the transaction is requesting for those data item that is available at the different site, it must be in serializable order with the context of global history. So if both the local history and global history is maintained as serializability, then and then we can say that globally serializability we can achieve. So this is the all about basic serializability and distributed serializability in transaction management. Thank you for watching this video.